My dear students, welcome to Easy BTech, your guide for BTech and beyond, and our subject Signals and Systems. And today's topic is Fourier series. Before going to our topic, please subscribe, share the channel. Very helpful to you. And in this channel, you can have all the subject videos, BTech subject videos, and you can learn subjects easily. You can understand subjects easily. Let's start our session. Fourier series representation of periodic signals. So let's discuss Fourier series representation of periodic signals. Fourier series representation of periodic signals. Fourier series representation of periodic signals. That means this Fourier series concept is applicable for periodic signals only. That is the first point. Fourier series representation of periodic signals or periodic functions. Periodic signals. And this concept given by Joseph Fourier is the scientist Joseph Fourier. So what is the meaning of Fourier series representation? And this concept is applicable for periodic signals only. Fourier series concept is applicable for periodic signals. This is the point for periodic signals. Periodic signals only. And we have continuous time Fourier series, discrete time Fourier series. So here we are going to discuss only continuous time Fourier series. Means Fourier series of continuous time periodic signals. So here we are going to discuss continuous time Fourier series. Continuous time Fourier series. So first of all, what is the meaning of Fourier series? That we discuss. What is the meaning of Fourier series? So Fourier series meaning is representation of periodic signal, representation or writing or expression of or representation of periodic signal, representation of periodic signal by linear combination of harmonically related sinusoids, or complex exponential functions or complex exponentials. Sinusoids or complex exponentials. Complex exponentials. So we can represent a periodic signal. We can write periodic signal using harmonically related or linear combination of harmonically related sinusoids, or harmonically related complex exponentials. So this concept is called as Fourier series. So here we have two types of Fourier series. The first one is Trigonometric Fourier series. And the second one, exponential Fourier series. Trigonometric Fourier series and the second is, in short form, we can say TFS, trigonometric Fourier series. And the second one, exponential or complex exponential Fourier series. So I am writing exponential Fourier series. Exponential Fourier series. So these are the two categories of Fourier series. Continuous time Fourier series we have. So it is in short form we can write as EFS. Now we discuss about these two, definition, and here we need to do evaluation of coefficients, trigonometric Fourier series coefficients, exponential Fourier series coefficients. That two we are going to see now. Let's see first trigonometric Fourier series. What is trigonometric Fourier series? Trigonometric Fourier series. So I am taking a continuous time signal x of t, periodic signal. Take continuous time periodic signal x of t. So x of t is a continuous time periodic signal with period capital T. What is the time period of this signal? We are taking as capital T. Continuous time periodic signal with a period capital T. Period capital T. So this signal we are going to express, or we are going to write. That is, x of t is equal to like a0 plus a1 cos omega naught t plus b1 sin omega naught t, okay, plus a2 cos 2 omega naught t plus b2 sin 2 omega naught t, again plus, so series representation, and in this series we are using trigonometric functions like sine cos. Are you observing? And a3 cos 3 omega naught t plus b3 sin 3 omega naught t up to infinity, and so on infinity. So this series representation of periodic signal. And here we have sinusoids, sine cos functions or sinusoids we have. They are harmonically related. How they are harmonically related is, so here we have frequency omega naught. This term is called, or this frequency omega naught is called fundamental frequency. This is called fundamental frequency. Fundamental frequency. And if you see the second term, a2 cos 2 omega naught sin 2 omega naught. So 2 is the integer multiple of fundamental frequency. Right or not? It is integer multiple of fundamental frequency. 2 omega naught, 2 omega naught. And this term is called harmonic. And here frequency is 2 omega naught. Therefore, it is called second harmonic. Because of frequency 2 omega naught, 2 into fundamental frequency. That is why it is clearly called as second harmonic. And here we have frequency 3 omega naught. Again integer multiple of omega naught. Omega naught is a fundamental frequency. What is omega naught? Fundamental frequency. Here we have 3 omega naught. So that is why this is called third harmonic. Third harmonic, and so on. Fourth harmonic, and so on. So we are representing periodic signal by linear combination of Linear combination of harmonically related sinusoids. Harmonically related sinusoids. This is called trigonometric Fourier series. This series is called trigonometric Fourier series. So instead of writing the total series up to infinite terms, we can use summation. So x of t is equal to a naught plus, what is the summation? Where to where we take 1 to infinity. So n is equal to 1 to infinity a n cos n omega naught t plus b n sin n omega naught t. Sin n omega naught t. So this is the meaning of trigonometric Fourier series. Trigonometric Fourier series. So here we have a naught. What is a naught? So a naught is called DC or average value of x of t. Average value of x of t. Average value of x of t over one period. Over one period. Over one period. Right? That is t. So this is the meaning of a naught. And similarly, we have an and bn. They are called trigonometric Fourier series coefficients. An and bn. These are called as trigonometric Fourier series coefficients. Trigonometric Fourier series coefficients. Okay. So this is about trigonometric Fourier series. Just simply we take the periodic signal and it is represented using linear combination of harmonically related sinusoids. Harmonically related sinusoids. Right? A naught is called DC value or average value of x of t over one period, and a and b and are trigonometric Fourier series coefficients. Now we have topic now, evaluation of Fourier series, trigonometric Fourier series coefficients. Evaluation of trigonometric Fourier series coefficients. So how to calculate or how to determine Fourier series coefficients, trigonometric Fourier series coefficients. So first I am going to do average value of x of t, a naught. So we have formula. I am writing formula. Then we have derivation or proof. So this is the formula: 1 by t integral 0 to t x of t dt. This is the DC value or average value of x of t. Whose average value? X of t average value. Now here limits over one period. Please remember, in all formulas, in all coefficients, trigonometric Fourier series coefficients or exponential Fourier series coefficients, limits are over one period. Integral limits are over one period. That means you can take 0 to t, or you can take minus t by 2 to plus t by 2. Right or not? One period. Okay? Don't get confused. So limits over one period. Now, to do this derivation, let's take trigonometric Fourier series. Trigonometric Fourier series. What is trigonometric Fourier series? X of t is equal to a periodic function or a periodic signal. X of t is equal to a naught plus summation n is equal to 1 to infinity a n cos n omega naught t plus b n sine n omega naught t. This is the bracket. Now to have formula a naught, what I am doing, you both sides x of t. This is the trigonometric Fourier series. You both sides do integration over one time period or one period. We can have a naught formula. Just both sides integrate with respect to t. Both sides integrate with respect to t over one period, over the limits one period. So here limits also important. Over the limits one period, like 0 to t you can take, or minus t by 2 to t by 2 also you can take. So I am going with 0 to t over one period, 0 to t. So here I am doing x of t integration both sides with respect to t. So integral 0 to t x of t dt with respect to t. So right side we have a naught. So a naught integration 0 to t dt, and we have summation 1 to infinite, and again integration of this an cos n omega naught t, an cos n omega naught t dt, plus again here bn you can write outside the integral, no problem, 0 to t sine n omega naught t dt. So this summation is for both the terms, an cos bn sine. So I am keeping bracket. If you evaluate it, if you simplify it, so here integration 0 to t means over one period or one time period, integration of cos. The value of this integration cos over one time period is 0. And similarly, sine is also 0. So only we have this term, and left side we have integral 0 to t x of t. So now, left side we have 0 to t x of t dt. This is the LHS we have on left side, and right side we have a naught, and the integration of 1 is t, and the limits 0 to t. So this will become a naught into t. We want a naught formula, therefore a naught equal to 1 by t integral 0 to t x of t dt. This is the average value of x of t, right? Simple formula, just integration 1 by t. Next we are going to see an formula, coefficients an and bn, right? Evaluation of an now to find an. So first I will write the formula, then we discuss the proof to find an. So an is equal to 2 by t, limits are integral 0 to t, here x of t into cos n omega naught t dt. This is the an formula. So if you observe the formula, we can get the proof by x of t only, right? You take the x of t, multiply both sides by cos n omega naught t, and integrate with respect to t over limits 0 to t. That is the process. The formula is saying the proof. Okay, so what is x of t? Trigonometric Fourier series. X of t is equal to a naught plus summation 1 to infinity an cos n omega naught t plus bn sin n omega naught t. sine n omega naught t. So this summation is for the both terms, an cos bn sine. So I am keeping bracket. Let's multiply both sides by cos n omega naught t. Multiply both sides by cos n omega naught t. After multiply and integrate with respect to t. This is the step we go. Integrate both sides. This is both sides. Integrate both sides with respect to t over the limits 1 period or 0 to t. This is the limits 0 to t. So this we are going to implement now. We are multiplying both sides x of t by cos n omega naught t. After multiplying, do integration with respect to t over the limits 0 to t. That's all. In this process, we get the an formula. So now x of t is multiplied by cos n omega naught t, right? And integrate 0 to t limits with respect to t. So right side also same. A naught is multiplied by cos n omega naught t and integration 0 to t dt plus summation 1 is equal to n is equal to 1 to infinity. So an you can write cos and cos, it will become cos square n omega naught t and integration 0 to t dt plus bn sine into cos, or right, bn integral 0 to t sine n omega naught t into cos n omega naught t dt. So summation we have bracket. Now we need to do RHS. So right side we have 3 integrations. Let's take is the integral 1, integral 2 and integral 3 or integration 3. So already we discussed these integrals. Integral 0 to t sine cos 0. Okay, and integration of cos 0 to t limits 0. So only this will remain. Already we have done this. So this integration answer is, what will be this integration answer? T by 2. In the previous session we have done it. It is t by 2. So t by 2 here an. This is the RHS. Right? Now by this we can have the formula of an. So an is equal to, send this t by 2 left side. It will become 2 by t. Integral 0 to t x of t into cos n omega naught t dt. Simple and easy. This is the answer an. Okay, understand? Just we multiplied both sides cos n omega naught t and integrate with respect to t over limits 0 to t. Then we get the an formula. Similarly, bn also we can do easily. To find bn now, how to get bn? First I will write the formula of bn, then we go for proof. So bn is equal to, same like an, 2 by t integral 0 to t, here x of t and multiplied by sine n omega naught t. The x of t is multiplied by sine n omega naught t. And go for the proof. So how to do is, first to take x of t, a naught plus summation 1 to infinite an cos n omega naught t plus bn sine n omega naught t. Right? This is the trigonometric Fourier series x of t. X of t Fourier series, trigonometric Fourier series. Now both sides you multiply x of t by sine n omega naught t, then integrate with respect to t over limit 0 to t. So that point I am writing. So both sides multiply x of t by sine n omega naught t and integrate with respect to t, over the limits 0 to t. So let's have this step. So integral 0 to t x of t, this x of t is multiplied by sine n omega naught t, and the right side also same thing. So a naught integration 0 to t sine n omega naught t, okay, and plus here an and summation n is equal to 1 to infinite integral 0 to t sine n omega naught t into cos n omega naught t dt. Okay, so I am writing here plus again bn 0 to t integral 0 to t sine into sine square n omega naught t dt. So again we have three integrations right side. So I am talking about RHS, right hand side integrals. So three integrals we have. Suppose this is the integral 1, second integration and third integration. So out of three, this integral already we know it is 0. This value is 0. And this value also, second integral also 0. So third integral, this value is t by 2. The third integral value is t by 2. Already we have done, we are using now. This third integral is t by 2. So now go to the next step. So integral 0 to t, the left side we have x of t sine n omega naught t dt is equal to, the right side we have bn t by 2. We want formula for bn, so bn is equal to 2 by t integral 0 to t x of t into sine n omega naught t dt. So this is the formula bn. Okay, so I am writing summary of trigonometric Fourier series. So trigonometric Fourier series is defined as trigonometric Fourier series. So we take a periodic signal x of t, its time period is capital T, is equal to a naught plus summation n is equal to 1 to infinity an cos n omega naught t plus bn sine n omega naught t. Okay. So here a naught DC value or average value of x of t. The formula is 1 by t integral 0 to t 1 by t integral 0 to t 1 by t integral 0 to t x of t dt, and an 2 by t integral 0 to t x of t into cos n omega naught t dt, and bn 2 by t integral 0 to t x of t sin n omega naught t, sin n omega naught t dt. Right? So here t is time period, letter t is the time period. Okay? Fundamental time period, the minimum time for which completion of one full cycle. The time taken by the signal to complete one full cycle, or minimum time period, is fundamental time period. And omega naught is fundamental frequency, and omega naught is equal to 2 pi f, and which is f is equal to 1 by t, so it will be 2 pi by t. Right? Fundamental frequency. Omega naught is fundamental frequency. Fundamental frequency. And time period is t is. Right? So here limits also, please remember carefully. Limits, integral limits over one period means 0 to t. How much? One period. Minus t by 2 to plus t by 2. How much? One period. Okay? Over one period. So please remember about limits also. So this is the summary of trigonometric Fourier series. Okay? So I am stopping here. We have next session. In that next session, we discuss exponential Fourier series. Again, we have exponential Fourier series coefficients, formula and derivation. After that, the relation between trigonometric Fourier series and exponential Fourier series. Very important session. So all of you please watch videos regularly. Thank you. Thank you all.